Okay. In our design, we were tasked to build a simple scissor jack assembly to be able to lift a maximum of 2,000 pounds. And talking about design requirements, we wanted the weight to be less than 15 pounds. After building a CAD model and applying appropriate stills to each of the different members, it came out to a weight of 12.67 pounds. We wanted it to be manufacturable, and we can see that each of the pieces in this design can be easily manufactured using traditional manufacturing techniques. We wanted it to be able to withstand an infinite number of life cycles so it can have a good long life. We wanted to actuate it by turning a screw, and we wanted to be able to raise it 6 inches. And so we can see if we change the configuration to raised, that the model does indeed raise up, and that would be about what it would look like in the raised position. And Daniel's going to talk about some of the verifications we did with the model.
All right, so we used MATLAB to validate the model. First, we did hand calculations, and then we ran it through MATLAB to make sure that they aligned. So we were able to validate the MATLAB model. We were able to calculate the forces within all the members across the entire range of length for the crossbeam. As you can see, the maximum force is within the crossbeam, which is to be expected since this is in tension. We're able to calculate the stresses of each individual stress component. We could see here that tear-out shear stress actually had the highest stress in any of the angled members, and the shear stress for pins and pure shear, because of our configuration, is the highest stress for the pins. So we were able to do the fatigue analyses on those two parts, and then we just assumed that all the other parts would have less stress, but being built out of the same material, it would have an equal or greater safety factor. And Mac is going to talk about those safety factors now.
All right, so these are the safety factors that Daniel was mentioning here that we got from our model. A couple key takeaways from this is the angled beam bearing stress, which is where we would start having the angled beams yield. The safety factor is 2.094, as well as the threaded rod in buckling would be 3.3, which these are both lower than the fatigue safety limits, which validates our model of infinite life, because these would fail statically before fatigue would occur. If you look at the maximum load predictions, you can see that 4,188 pounds is the max load that this jack assembly could actually withstand before any deformation would occur, which we feel is valid, especially in a construction or farm setting where misuse may occur. As far as the materials used, in the angled members, we would be using a 1040 steel, as well as the top and bottom plates. 1080 steel would be used for the cross beams, and a 316 stainless steel would be used for the pins. More information on each of these materials can be found MatWeb at these links. And Alexa is going to talk a little bit more about our validation of the model.
So we ran the FEA model, and the top one is the displacement that was found when the 2,000 pounds was being pulled on the jack when it was fully extended. The displacement is very minimal in inches, and so it's well made for sure. And then the second one shows the von Mises stresses and what actually happens, looks like in the model. But then this second one down here is colors are adjusted to show more readily the places of stress that would come over time. However, even with this, the colors are adjusted to be to less than half of what the max stress experienced is. And So this further proves that our analysis in MATLAB and our tables and our safety factors that this jack is well made and is well done. Thanks for watching our video.